name is Aljoscha Krettek. I'm from TU Berlin, and I'm going to talk about enabling operator reordering in data flow programs through static code analysis in our stratosphere system today. So for this, I'm going to first introduce the context in which we work and give a bit of motivation for what we're doing. Then I'm going to talk about operator reordering, why it's necessary. Then I'm going to give our approach where we use static code analysis to enable this operator reordering, and then I'm going to give the conclusions. So, big data analytics. The field where we work in is big data analytics. We have huge data sets, normally, for example, from click streams or from biomedical data or classical data warehouse data and so on. And we need to perform deeper analytics on these very large data sets on distributed classes of machines. And for this, a new method or a new idea of parallel data management systems have come up. And the first idea to come up is probably MapReduce, which is also based on functional programming ideas. And then there are other systems, the Hadoop system, which is MapReduce implementation, open source. Stratosphere, which is our system, and I'm going to talk about this a bit more, and then other systems from other universities. And what all these systems have in common is that they are a data flow. And in these data flows, you have operators that operate on this data. It's the common theme. And also, currently we see these ideas coming up in massively parallel processing SQL systems, for example, FreeCom systems and SS systems. And the general idea of what we want to do is, because SQL doesn't give us the means to do the deep analysis of unstructured data such as text logs and so on that we require today. That's why we have these systems. That's an overview of our system, stratosphere system. What we have is a compiler that compiles from a query language to an intermediate representation. Then we have an optimizer that tries to optimize this data flow, and then it's executed on a distributed execution engine. In our case, this one is called NetLink. And it's meant for scaling to very large clusters of computers. The programming model that we have in our system is it's a generalization of MapReduce. I'm hoping people know what MapReduce is. Yeah. So in MapReduce, we just have the fixed pipeline of data sources, map, then shuffle and command phase and reduce, and then the output. But in our system, what we have is we have a general data flow with sources at the bottom. Then we have several operators in data flow. You combine this, and then at the end we have sinks. And what these operators are is they consist of a second order function, and we have a fixed set of second order functions. So for example, map is a second order function, and reduce, these are the same from MapReduce, and then we extend this with three other second order functions: match, cogroup, and cross. And it's not necessarily what I do right now, but for example, with match, we can implement joins in data flows. So match, so for map, the first order function that is written by the user in Java code is called once for every tuple. And in match, the first order user-defined function is called for every two of the inputs. It's a binary operator. It's called for two input tuples where attributes in this tuple match. And I've got that. In our data model, we have so the records that flow through the system are, you think of them as tuples, and you have several attributes. Yeah. And what's important to notice also is that this PAC programming model, where you have data flows and user-defined functions in Java code, is an intermediate representation, because normally you would write query in our query language and it's compiled down to this intermediate representation, optimize it, and run on the NetLink engine. But you can also use this to implement functionality that is not implemented by the query function. So this is where it gets more powerful in SQL, because you can write general purpose code in these operators. So what the system can do right now, we have this fixed data flow, and what we can do to optimize runtime speed is we can choose physical optimizations for the execution. So for example, match, which is you can think of as a join in the SQL system, we can choose whether we want to broadcast, or which side we want to broadcast, or whether we want to do a fragment replicate join and so on, or which merge, or which join method, sort, merge, hash base, and so on. So this is what we can do, but right now, up until now, we could not reorder these data flows, such as an SQL system might do, because it knows the algebraic properties of the query. So what we want to do is, from this query to this query, as you see, we moved the reduce, which is aggregation property, from after the join to before the join. This greatly reduces, or might greatly reduce, the number of intermediate records that have to flow through the system. And they also might introduce new opportunities for different physical join strategies and so on. And it's also, I think, clear from classical SQL style query execution that changing the order of joins or pushing down aggregations and so on can greatly improve performance. And what also is interesting here is, because we are a general purpose system and you can use general purpose Java code inside these operators, it's not sufficient to know the signature of these operators, of these second order functions, but we also need to look inside the user code to decide whether we can reorder these operators or not. These are just some numbers to motivate what we're doing. For example, TPCH query number 7 is a query that has a large number of joins, and it's obvious that if you have a bad join order, you have a very large runtime compared to when you have a good join order. So this is also what classical SQL systems can do, but then we have other workloads. The clickstream workload is, for example, a data analysis use case where we analyze unstructured, where we analyze click log, and the text mining use case is text mining case where we look at unstructured biomedical data. And this is something that our system can do. We can also reorder data flows and have huge performance increases here. And this is not possible with classical systems. So what we discovered, or what we noticed, is that we need to have a certain set of properties of the user-defined code is inside these operators and data flows to be able to reorder them. And for this we need several definitions. We need the read set. The read set is a set of attributes of these records that come into operators that might possibly influence the output records of this operator, and the write set. The write set is a set of attributes that might be changed in these records as they flow through operators. We have several proofs for this for all kinds of operators in the system, but as an example, just look at map reordering. We can reorder two maps if they operate on distinct attributes of the tuple, so if they only read attributes, for example, that are not written in the other operator, and so on. And what also is obvious, we could ask the programmer to just specify these read and write sets, because the programmer obviously should know what he does in his function. But we also want to be able to optimize lexicode we don't want to ask the programmer to have to specify this. So we want to look inside the user-defined code and use static code analysis to derive estimates of these read and write sets. So yes. So I'm going to describe now how we derive these read and write sets by looking at an example user-defined function. This one is for match user-defined functions. Then we have two inputs, left and right, and we just emit something at the end. I'm going to go through this step by step, so don't worry right now. But what's needs to be noticed is that we're dealing with a fixed API here for modifying these records that go through the system. That's why we are able to do this even. And this API is we can create new records. This is not seen here. We can create a new record by copying an input record. This is seen in line 4. And then we have get, set, and set null for getting attributes out of records and setting attributes on this record. The first thing which is easy to notice is that the read set can easily be determined by just looking at all cases where get of an attribute is called and just add all these to the read set. But the write set is more difficult to derive because the write set, as we'll see in a minute, depends on the position of the operator in the data flow, because it depends on what attributes the tuples that come into the operator have. Yeah, that's basically what it depends on. And therefore we need to determine for other sets, which I'm going to mention in a second, and then generate a final write set from these. And I'm going to go step by step through this to show you what it looks like. So to derive the final write set, we derive 4 other sets, which is the origin set. And the origin set tells us from which side of the input of the operator the tuples come. So we see we have the emit call, which emits the final record for the next stage in the data flow. And this record is created in line 4 by copying from the left. So in the origin set we have 1, which is 1 is the first input, 2 is the second input. That's all the origin set tells us. Then we have the projection set, which tells us which tuples are explicitly projected out from the record by this operator. And we see here line 8 called set null on our tuple. So attribute A is in the implicit projection set. Then we have the copy set. Oh, by the way, the projection set. Oh no. Then we have the copy set, which tells us which attributes are explicitly copied from the input tuples to the output tuples or records. As we see here, we have E in the copy set because E is called in any case. So we call set attribute E by getting attribute E from the right input. What's also interesting here is we have in line 6, we also set attribute D to an attribute we get from the right input, but because this is inside an if statement, we're not sure that in any case, or in any run of this function, the attribute is copied. So to be safe here, we just add those attributes that are executed in all cases of the execution of this operator. Then we have the explicit write set, which just tells us which attributes are explicitly changed to some other number that is not read from any attribute of the input records. And from the schema information we have, so in this example, the records that come in from the left have attributes A, B, C. Records from the right have attributes D, E, and F. This is schema information, and from this and our sets we can derive the final write set. So for the write set for records coming from the left, we notice that 1 is in the origin set, so records always come from the left, and then we remove, and then we add A to the right set because it's projected out, we set null, and we F to the right set because we just write some random number to it. And for the right set, for the right input tuples, we notice that this is not in the origin set because it's not the output record is never created from this input record. So we add initially all attributes, D, E, and F to this right set. But then we notice that in line 10, we explicitly copy attribute E from the right input record, and therefore we remove this from the right set. And then we arrive at these final right sets. And difficult part now, so I think for humans it's very, very easy to derive these sets by just looking at simple examples, but what we're going to do is we want to analyze Java bytecode to determine these sets, and it's I think difficult part of this work. So we're working on a control flow graph. This is just a function that I showed you earlier. And the solution that we came up with is that we start from the emit statements, walk up recursively to either copy statement or create statement, and then have for each node in this graph origin, write, copy, and protection set. And these sets depend on the nature of the statement that we're looking at, and the sets that are coming from the statements higher up the control flow graph. So I'm going to show this in the next slide. Here, for each statement it's shown the sets, and since this is recursive, we start here, then go all the way up, and then from there the recursion unrolls again. So for the first tuple we see it's created from the input record, so we have one in the origin set and so on, because it's a copy statement. And as already said, for the other statements, we merge the input sets, and then depending on the nature of the statement we're looking at, we do different things. So if it's a set call, where we set an attribute that we get from the same position in the input record, we add this to the copy set because we explicitly copy it from the input to the output. If we have a set call that just sets it to some random value, we add it to the right set because we can't know where the value is coming from. And if we have set null, we add this n to the projection set. And then merging all these sets from top to bottom, we arrive at the final result that we also got from looking at the function as a human. So finally, what can be said then is that reordering can lead to significant benefits. It's also known from SQL execution, where we know that reordering joins can lead to massive improvements. But our method can derive or can automatically optimize and reorder data flow programs with generic user-written Java code. The difficulties that we have is mostly conditionals and loops. As I showed you, because these are tricky. We achieve safety through conservatism. As I showed you, for example, we only add attributes to the copy set if in any execution of the user code these elements are copied. And then finally what I want to mention is a related work, Manimal, which also uses static code analysis in the MapReduce framework to derive where it would be useful to use an index, I think, to speed up MapReduce processing. And this can also use complementary with our system. So that's it. Thank you for the attention. And the Stratosphere system is also available at www.stratosphere.eu. We just had a new open source release, but this reordering code is not yet in there. So, thank you.
but you discussed how to use static code analysis to construct these 4 kinds of sets, right? Copy,
Yes.
write, projection, and origin sets. So the 4 sets. So, but did you discuss how to use this this information to actually reorder for, let's say, making it more parallelizable or something?
Sorry, what was that part?
So how do you use these sets to, how do you reorganize these sets once you get these sets?
How to derive the final write set, or how we use read and write sets to then do the reordering?
Yes. How do you use these sets to do the reordering?
Yeah, we actually have another paper that we just presented at DRDB, where we have proofs for this reordering and how we do the actual reordering, but we didn't mention how to derive these sets, and this is how we derive these sets. But how it's done right now in the system is that we look at step by step at 2 operators next to each other and look whether we can reorder them, and then do an enumeration with these. So it's still rather simple because we're still working on it, to be honest.